Welcome to my presentation about resonance, viscosity, and mass density sensors. In this talk, I will talk about achievable accuracies, and I want to start with our motivation for these sensors right away. Usually, rheologists use oscillatory experiments to determine, for example, the spectrum of complex viscosity. And the reason why I show you this chart is to make you aware about the frequencies they're able to perform the experiments. So in this case, it's very typically, it ranges from several millihertz to, let's say, some hundreds of hertz. On the other end of the spectrum, there is the well-established quartz crystal microbalance, which is usually operated in the megahertz range. So between these two devices, there's a large gap between 100 hertz and 1 megahertz, which we are aiming to bridge with our devices. Furthermore, we want to develop viscosity sensors and not instruments. And once you are able to develop a sensor, these other arguments will be nice side effects. So low cost handheld devices, and they also will allow inline measurements. This is an overview of principles we looked in the past at. So we had oscillating membranes, straight beams or straight wires, shear oscillating platelets, tuning forks, and such U-shaped wire, we call it U-shaped wire, which should come close to a single clamped structure. All these devices can be explained and described in common by a lumped element oscillator, which is exposed into the sample liquid. And easily speaking, higher viscosity, if you record the frequency response of the resonator, higher viscosities yield higher damping, whereas higher mass densities yield lower resonance frequencies. Now I want to show you measurements with first approaches, setups, and problems we had with these setups. So for the three structures which you see on the top left, these are double clamped structures. And these double clamped structures have the disadvantage that they are very cross sensitive to temperature. What we see here are the evaluations of resonance frequency for the case of a straight wire. And in the first example, we really had a huge cross sensitivity to temperature. We were able to drastically reduce this cross sensitivity to temperature with sophisticated tensioning mechanisms. However, as you can see in these figures, the stability of the resonance frequency was really bad. So we even got non-reproducible results for the resonance frequency over temperature. That's why we come up with a completely new idea, making everything simpler and stabler and aiming at the single clamped device. The idea of this concept study was to have a measuring cell containing both a mass density, so a separated mass density sensor, and a viscosity sensor. The mass density sensor should consist of an oscillating tube, whereas the viscosity sensor should consist of an U-shaped wire, which is immersed into the liquid. And maybe those who are familiar with mass density sensing, they will see that the mass density sensor is very similar to the commercially available CMA 5000 from Hanson Bar. However, we wanted to make this device smaller, easier, and follow a cost-efficient production process. This was the first, these are just pictures of the first prototype of this mass density sensors. So we used a stainless steel tube with a diameter of about 1 millimeter. And again, the sample liquid was inside. And these are first results of the mass density sensor. So what you see here are evaluated resonance frequencies over mass density. and the function above is the function of the black straight line. And as you can see, we see a deviation of the resonance frequencies from the model, and this deviation gives the indicated inaccuracy of the device. And if we compare this accuracy with commercially available devices, we see that for handheld devices there we still can improve for a factor of 10, and for laboratory instruments, yeah, the accuracy is really high, but we cannot really compare the laboratory instruments with handheld devices at which we are aiming at. But still, if we improve the setup, it should be feasible to make the accuracy 10 times better. One limiting factor for any resonant sensors, in my opinion, will always be the accuracy of the temperature measurement you have to do in any case, because you will always have a cross sensitivity to temperature. In this case of this sensor, the cross sensitivity to temperature is indicated here, and if we want to achieve the 1 milligram per cubic centimeter, the accuracy of temperature measurement should be 0.6 Kelvin, okay, which is quite feasible. However, if we want to achieve the aforementioned 10 microgram per cubic centimeter, the temperature measurement the accuracy should be 6.4 millikelvin, which I hope you agree with me would not be possible. So in this case, you have to think about how you can, on the one side, increase your sensitivity to the quantity you want to measure, in our case, the mass density, and reduce your cross sensitivity to temperature, for example, with different materials. Now I want to switch to the viscosity sensor. The viscosity sensor we built, as I already mentioned, was a bent tungsten wire, which was braced into solid brass blocks. Everything was put in a solid aluminum housing. We applied a PT100 temperature sensor close to the wire, and yeah, put everything in a closed an aluminum chamber to prevent from evaporation. The structure was the device was put in a climate chamber and controlled at 25 degrees Celsius. These are first measurements, recorded resonance frequency responses, which are also in our paper, and the evaluation of the quality factor of these measurements over viscosity is depicted here. And again, the measurements deviate slightly from the model, and the result of this experiment shows that we are within a margin of, let's say, 5% accuracy. And if we now recall the factor of 10, which still should be possible to increase the accuracy, which we know from the mass density sensing, because we could compare it with commercially available devices. So it should be possible to achieve accuracy lower than 1%, and once you achieve that, you really compete with laboratory instruments. So their accuracy is around 1%. Finally, let me address some issues we are still facing at, and this is long-term stability. For most of our devices, we did long-term measurements. We put these devices in ethanol at 25 degrees Celsius and did nothing more than continue measuring, for example, for the first device for a week. Okay, and however, like the resonance frequency is pretty stable, so the variation is 0.4 hertz at roughly 1 kilohertz. What is strange is that we still observe a trend in this variation of the resonance frequency and also in the quality factor. And right now we cannot really explain that, and in many papers also people address that you have a noise on resonance frequency and quality factor. So we really have to find out where these trends come from, and if possible reduce these trends. However, like resonance frequency is pretty stable, so we have 0.4 per mil in case of the oscillating wire. Tuning fork, which is assumed, so we examined the tuning fork because it was supposed to be a really stable resonator, which was surprising for the tuning forks that it varied a lot in the quality factor. So the variance, which is more or less random, was 30% in case of the tuning fork. Okay, so finally, let me conclude my talk. I gave you an overview of principles for viscosity and fast sensing. I showed you that for first prototypes, we achieved accuracies for 10 milligrams per cubic centimeter and 5% for the viscosity sensors. And as an outlook, we are aiming to get accuracies for 1 milligram per cubic centimeter and 1% for viscosity. And I hope that we will achieve that. Okay, thank you very much for your attention, and